Hi everyone, this is Mr. Chiu again, and to begin with, I need to mention that whatever I'm going through now is going to be the advanced component. So it's not going to appear in your IB exam questions. It is going to be in the advanced papers that you will be facing. And to be able to understand and appreciate this, whatever I'm going to do very soon, you need to be able to understand phase difference. So please check out my micro lesson on phase difference before you listen on to this, whatever I'm going to go through right now. So let's take a look at the two source interference that we discussed earlier on. Say for example, you got two sources with waves traveling and meeting at point X. The angle is theta, but please bear in mind that this separation is usually very small compared to this. So this is almost parallel, not parallel, but almost parallel. This distance over here is d, and we drop a perpendicular line over here. So what is the additional distance that this light ray over here or sound waves over here is going to travel? This is the additional distance because this is going to form an isosceles triangle with this. I know it's weird that this is right angle, and then how on earth do you have an angle over here? So please remember that this is almost parallel. This angle over here is almost zero. So this is approximately the path difference over here. Now, if you use a little bit of trigonometry, this is 90, this will be 90 minus theta, and this will be theta. So this is the opposite over hypotenuse. So this path difference, which is the opposite over hypotenuse, is going to be sine theta. So path difference is going to be d sine theta. Okay, and just now I mentioned in the previous lesson that there is this phase difference, which is phi equals to 2 pi d sine theta divided by wavelength. This is the separation in distance between these two waves. So this will be the phase difference between these two waves over here when they meet at point X. Now this is the part where you need to, where I'll be showing you a method called the Phasor diagram. So how do we add the influence due to each of the two waves at this point? Now this is the Phasor diagram method. So we represent, say, the wave from S1 as x0, x0 being like the one that we use in simple harmonic motion, the amplitude. So how do we represent the influence by these waves from S2? So we offset the wave from S2 by an angle of phi. So we represent, in the Phasor diagram method, we represent this phase separation between the source, the waves from S1 and S2 by this angle over here. It's almost like a vector kind of offset, where you offset the angle by phi and x0, because both waves has amplitude x0. I'm sure that you have guessed by now that the resultant wave has an amplitude of xr, which is from here to here. So this is the Phasor method to find the resultant amplitude. Take a look. This is an isosceles triangle, so this angle will be the same as this angle. And this plus this must be equals to this. So I can conclude therefore that this is phi upon 2. And therefore, if we do a little bit of trigo over here, I'm sure they can see that xr divided by 2, which is this length over here, divided by x0 is going to be cosine phi. Hence, xr is going to be 2x0 cosine phi. So this is the resultant amplitude over here. And if we square the amplitude, we are going to have intensity proportional to xr squared, which is proportional to 4x0 squared cosine squared phi. And hence over here, if we compare to the intensity of each of the wave, which is called I0, it is proportional to x0 squared. So combining these two, we can say that the intensity resultant is equals to 4 times the intensity due to each wave times cosine the phi upon 2 over here. Phi upon 2, phi upon 2. Sorry for the mistake. It should be phi upon 2, and therefore it's cosine squared pi d sine theta divided by lambda. And if you were to plot this wave, this pattern over here, in terms of angle theta, that is that if you sweep this angle over here, you're going to get this pattern over here. and hence this is what you see for a two-source interference pattern, which is the Young's double slit pattern. So this is what we call the Phasor diagram method, which you actually add influence due to the two sources using a vector triangle like this. So this is one of the method that I'm going to show you. There's a second method. Now some of you may ask me whether it will work whether you have 2 waves, 3 waves, 4 waves. Yes, it works. So you can use it for 3 waves, 4 waves, or n number of waves. It just gets a little bit more complex mathematically. In fact, it doesn't get a little bit more complex. It gets much more complex when you have, let's say, 2,000 waves. So there's this method which is using complex numbers that will actually provide a much neater and more elegant mathematical solution to the problem that you face when you have a lot of waves. So let's see how this complex method applies. So if you were to take a look at if you were to reference the previous discussion that we had regarding using complex notation for representation of waves, we can represent a cosine wave as in terms of x naught e to the power I omega t. And therefore what we have over here is representing the contribution of the wave at this point in terms of this expression. So we call it x1 due to source 1. x2 is no longer just e to the power I omega t, but plus a phi, because there is a phase difference for the wave coming from S2 is lagging behind by a certain phase. So when we add xr, which is x1 plus x2, you will have this resultant wave, which is I omega t plus phi. Now what you have over here is, what you can do over here is to factorize this thing out. I'll show you why you take phi upon 2, but if you were to factorize this out, you end up with a minus I phi upon 2 plus e I phi upon 2 times this factor over here. And therefore, if you were to take a careful look at this one, if you know your complex number, this will become xr equals to 2x naught e to the power I omega t plus phi upon 2 and multiplied by cosine phi upon 2, which if you were to convert it back to the as you can see over here, this is the cosine function, which is 2x naught cosine phi upon 2. I brought this part towards the left, and this will be cosine omega t plus phi upon 2. And can you see that this is the non-time varying factor, which is therefore the amplitude. So the intensity is proportional to xr squared, which is proportional to 4x naught squared cosine squared phi upon 2, which therefore we can say that it is 4 times the original intensity cosine squared phi upon 2. And this is identical to what we proved just now. So this is what we call the complex method, and the previous one is the Phasor diagram method. There's no one method better or more powerful than the other method. It is just sometimes it is easier to understand for some people. For some methods, it is better for some people because it's more intuitive for some. And for some people, it clicks with their way of thinking better. There are certain situations where one method is better than the other one. So I'm just showing you both methods so that it improves your arsenals of tools in solving complex problems. So in summary, we can actually understand interference fully using either the Phasor diagram method, which I showed you just now, and the complex method. So those are two very powerful methods that can be used in many situations, even sometimes in electrical waves. All right, so this is basically the method that I wanted to show you. It is an advanced portion, so there's no need for you to know this in the IB exam, but something that will be very beneficial for you if you want to ask why is the double slit interference pattern like this. Okay, so enjoy.